Hello, everyone. I will introduce LAMDA, our learning assistant multi-stage inference-based autotuner that accelerates FPGA design closure. I will start off with an example motivating why configuring CAD tools may be crucial for efficient design closure. The figure shows the distribution of timing results across various CAD tool configurations, where each marker corresponds to a design point with a unique tool configuration and timing target. And the start markers correspond to default tool configurations. There are two important observations from this figure. First one is default timing is 15% worse than the best timing observed. And second, more than 30% of the randomly sampled configurations result in a better timing than the default configurations. So these observations suggest that there is significant room for timing improvement through tool configuration. The size and complexity of the search space, as well as the time-consuming evaluation of each design point, makes efficient design closure highly challenging. That is why a number of autotuners have been proposed for automatically optimizing compiler configurations. Still, the challenge with the existing autotuners is iterating over this time-consuming CAD tool flow, which consists of logic synthesis, mapping, packing, placement, and routing stages. Therefore, we explored possible speedups that can be achieved by leveraging machine learning within autotuning. If we estimate timing without running through routing, runtime reduces by 60%, corresponding to 2.5x potential speedup. But this introduces some error in timing, and suppose that the corresponding root mean square error is E. If we estimate timing one step earlier, which is pre-placement, potential speedup increases to 14x. However, the error in timing estimation increases by 20%. And if we move timing estimation all the way up to pre-synthesis, we would be observing the highest error, which is 60% higher than estimating pre-routing. These scenarios illustrate the trade-off between computing effort and estimation accuracy. So to balance this runtime accuracy trade-off, we leverage multiple fast and low-cost design stages to estimate timing early in the design flow. The features of our estimation problem becomes tool configurations as well as the design-specific information we extract from these fast and low-cost design stages. And we use XGBoost, which is a very powerful grading boosting algorithm, as our regression model to estimate worst slack. Now I will briefly introduce the framework of LAMDA. In each iteration, we let our autotuner propose certain number of configurations. And LAMDA runs the fast and low-cost design stages, as we discussed in the previous slides. Tool configuration, as well as design-specific information, are used to estimate for each of the proposals. And then LAMDA prunes these proposals based on the timing estimations. Then top-ranked proposals are run through end-to-end tool flow to get the actual timing results. Due to lack of labeled data and cost of collecting end-to-end data, we supported our framework with online learning, where we periodically update our machine learning model with newly collected design points throughout the autotuning process. For evaluating LAMDA, we implemented 3 additional modes of ML-based autotuning. So modes that leverage early state features are referred to as multi, whereas others are referred to as single. And modes that utilize online learning are referred to as online, whereas others are referred to as offline. We also compare with the Ecenur, which is an open source autotuner. The global best plot shows best timing results achieved by each autotuner over time. First, we can see that LAMDA converges faster than online single, which illustrates the effectiveness of multi-stage learning approach. Second, we can see that LAMDA converges faster than offline multi, illustrating the effectiveness of online learning. And finally, LAMDA outperforms the Ecenur owing to its multi-stage online learning-based approach. And these are the average speed-up numbers we achieved over 5 designs. The global mean curve shows the mean of all timing results visited over time. Average for LAMDA is higher than online single, which supports our previous conclusion on the effectiveness of multi-stage learning. And average for lambda, as you can see, increases over time and then converges to a value higher than offline multi, which supports our previous conclusion on the effectiveness of online learning. So to understand why multi-stage learning and online learning increase the auto-tuning efficiency, we will have a closer look at the timing estimation throughout auto-tuning. In the first figure, each marker is a design point visited by an auto-tuner. X-axis represents actual worst lag, and Y-axis represents worst lag estimated by the ML framework of the corresponding auto-tuner. Design points of multi-stage learning-based approach are much closer to the linear line, which means that the timing estimation is considerably more accurate if we leverage early-stage features. And in the second figure, design points of online learning-based approach are closer to the linear line, meaning that timing estimation is improved if we utilize online learning. So that is the end of my presentation. We already had the poster session, so I will be very happy to chat with you over the breaks. Thank you for listening.